Starting to get a little bit more complicated now. So the robot's traveling 40 mil at 30 degrees anti-clockwise from the x-axis, and then for 30 mil at 15 degrees clockwise from the y-axis, so clockwise this time. State the magnitude and direction of the resultant vector. So I've done this one to scale, just to save a little bit of time, so you're not sitting looking at me drawing. I've used a scale of 15 divisions on my ruler is equal to 10 millimeters. Just double checking this time. Or millimeters, yeah, so we're working in millimeters. This must be a very small rover. Anyway, so 15 divisions equals 10 millimeters. So then I've drawn that out. So we've got 30 degrees, and I should probably put on the direction. So it's going anti-clockwise from the x-axis, and then we've got 15 degrees, but it's clockwise from the y-axis. So those are just two vectors. And so we put them nose to tail. So again, with displacement vectors, this is easy because it just is what happens. And so we've started with little rover. He's gone, or it's gone 40 millimeters in this direction. Then it's gone 30 millimeters in this direction. I just need to write on that that's 30 millimeters. It's going to be a little bit short of space, so I'm going to try and write that sideways. So 30 millimeters in that direction. Like I say, so when you're doing displacements, it just is what it says. So it travels that way and goes this way, but you can do this for any vector. You just take the vectors, put them nose to tail, join them up like that. That's how you find the resultant vector of those two vectors. So yet again, that resultant vector is just a vector that goes straight from the start point to the finish point. Let's move them out of the way. I'm going to draw this in black because we're going to do some components of this as well. Now there's a heap of different ways you can do this. Just showing the direction. It's a little bit small. So let me just get a decent arrow on that. Sometimes for the resultant they'll show two arrows. Another thing sometimes people will do for vectors is rather than show the arrow at the end, they'll stick the arrow in the middle somewhere. Either way is fine. In this course we'll usually just draw the arrows at the end. It's more common for forces and so on. Okay, so get that ruler out of the way. So the first thing we could do is just do this by scale, just to get some rough ideas. We can use that to check our answers. And again, if you're in an exam or something, this is pretty useful because you can just check your answer. And so let's see how many divisions we've got for the resultant. So we've got 10, this is just the divisions on the ruler, it's not the actual distance. So we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, and now we've got 95, 67, about 98. So we've got 98 divisions. So we need to change that into millimeters. Well, 15 divisions is 10 millimeters. So if we divide that by 15, we're going to get how many 10 millimeter segments we've got. So times that by 10. And so we're going to get, let me just double check, I think I might have calculated that already. So 98 divided by 15 times 10 centimeters. Oh, sorry, millimeters this time we're working in. And the answer is 65.3, so it's not going to be very accurate, so we'll just say 65 and we're working in millimeters. Okay, so that's just playing with this is just working out the scale from the ruler. So remember we said 15 divisions is 10 millimeters, and so we're just figuring out the total number of divisions was 98, divide it by 15 and then times that by 10 and you're going to get the equivalent distance. The angle is roughly 49 degrees. So this time we're going to do it by trig. We're not going to put this as an answer, but we're just going to note that to the side so that we know what we're expecting to get. So we can check if we've got roughly the right answer. So 65 millimeters. What did I say it was? 49 degrees. And it again is anti-clockwise. Okay, so we'll keep that in mind as we're doing our calcs. Now, the last example was quite easy because we had x and y components, so we got right angles straight away. This time is a little bit more tricky. And so the two component vectors we've got, so these two vectors here and the resultant, the component vectors and the resultant don't make a right angle triangle. There's no right angle in here. So we've got a triangle, but we've got no right angle. There's different ways you can do this. If you know a few other trig rules, you can figure it out just from this triangle. But the way that always works and the way that's easy to program into computers or into an Excel sheet or something like that is just to break these down into their components first. So what I'm going to do is figure out how far along the X and Y axis would I have to go to get along 40 millimeters. To get this displacement vector in this direction with a magnitude of 40 millimeters. And how far in the X and Y direction would I have to go to get this vector. And so essentially we're resolving these vectors into their X and Y components. That's what it's called, resolving the vectors. So I'd have to go along like so in the X direction for this first vector, the 40 millimeter vector, displacement vector. And then I'd have to go this way to get to that point. So in order to combine these vectors, we're actually breaking them down further. We're breaking them down into their components. And then what we'll do is we'll just add the components together. Okay, so then for this vector, we're going to have an x component of that vector like so. And we'll have a y component of this vector like so. So all of these things are equivalent. So if we had our little robot, so to get from the start to the finish, it could go straight along the ultimate resultant vector, or it could go along the two components where vectors were given, or it could go along the x and y components of those vectors. So go along here, along here, up here, and we still get to the same point. So all of those vectors are equivalent because when you add them all together, then you get the same resultant vector. So what we'll do is we'll calculate these x and y components, and then finally, I need to find another color. We'll do it blue this time, and it's awfully big. So eventually, I'm just going to draw these off to the side a little bit, but eventually we're going to calculate the x and y components of the resultant vector. Like so. And once we've got that, we'll be able to calculate the resultant vector because that's now a right angled triangle with that vector as the hypotenuse. So we'll come back to that in a minute. Okay, so let's give these some names first. And so we'll call this vector 1 maybe. And so we'll call this fx1, fx2, fy2, because that's the y direction. fy1 is the first vector. fx2, the x component of the second vector. fy2. Why am I calling them f? I'm thinking ahead to when we're doing forces. Sorry. Simpler than that. x1, y1, x2, y2. Okay. So now we've got a couple of triangles. We've got one triangle here. So we've got, and it's a right angle triangle, so it's got along here, up here, the resultant here. Then we've got another right angle triangle here, triangle 2. Along here, up here, with the vector here as the hypotenuse, or the resultant vector. Okay, let me just move the little robot. So what we're going to do is we're going to calculate all of these components, and then we know that the x component of this resultant vector is just going to be x1 plus x2, so it's going to be coming along here, and the y component of this resultant vector is just going to be y1 plus y2, so this distance up here. So let's do that. Usual stuff. Where's the right angle? And so this is going to be hypotenuse. This is going to be opposite. This is going to be adjacent. First thing we want x1. And so we've got adjacent and hypotenuse. So it's going to be cos. So we know that cos 30 degrees is equal to adjacent over hypotenuse. So cos 30 degrees is equal to x1 divided by 40 times both sides by 40 and swap them around. You get 40 times cos 30. Stick it in the calculator. I always forget my brackets. 34.64. And I'll just keep it 4 significant figures just now because we're going to use it later. So I'll round it down to 3 later. I just want to keep it a little bit more accurate. And then I might just move that down here as well, just to make some space to keep this tidy. So then we're going to get y as well. We'll still use the hypotenuse because that's what we're given. So opposite over hypotenuse, so it's sine. So sine there. Now we just have to, yeah, we're still in that one. So sine 30 degrees. So opposite over hypotenuse. So sine 30 degrees is equal to opposite over 40. So x1, so opposite is x1, times both sides by 40, swap them around. Not x1, y1, sorry. y1 is equal to 40 sine 30 degrees, which is equal to 40 times sine 30 is 20 exactly. Yes, it is actually, now I think about it. It's 20 millimeters. Okay, so what have we done? We figured out x1 adjacent over hypotenuse, so we used cos, and then we figured out y1 opposite over hypotenuse, so we've used sine. Okay, now we'll move on to triangle 2. So we have to be careful, this angle's not in the triangle at the moment. There's a couple of rules you can use. The first one is we could figure out this angle here. So just draw it on. So this angle plus this angle must equal 90. So therefore that angle there must be 90 minus 15, 75 degrees. Another rule you can use, you might remember that you've got a Z rule. So if you've got two lines and they're parallel, you've got another line crossing them, then this angle is the same as that angle. So this angle here must be 15 degrees. It's the same as this one. So that line is parallel to that line, therefore those two angles must be equal. So you can do it either way, it doesn't really matter. It's going to be hard for me to rub that out, just leave it there. I'm just going to get this one. So that must be 75 degrees. Okay, that's there. So this is hypotenuse. If I use this one, this must be adjacent and that must be opposite. Okay. So for x2, we need adjacent to hypotenuse, so we're on cos. Cos 30 degrees. There's one more thing I'll just point out here while we're here. One of the reasons that I always write this out is because it's not always the case that for x you use cos and y you use sine. And maybe I'll just use the other angle just to show you that. So I was saying you could have done your parallel lines rules, and then we would have used this angle here is equal to the other angle down there. And so if we had used this angle, then this would have been opposite and this would have been adjacent. So then when we're calculating x, we'd have been using opposite over hypotenuse, which would be sine. And so that's why I always write this out. Depends on the problem. Sometimes you can end up with sine is needed to calculate the x value. Just depends on what angles you're using. So sine 30 degrees is equal to opposite over hypotenuse, so katoa, so, and so sine 30 degrees is equal, where did I get 30 from? Sorry. So sine 15 degrees, it's this angle here. So sine 15 degrees is opposite hypotenuse. Sine 15 degrees is x2 over 30. So therefore x2 is equal to 30 sine 15, which is equal to 30 times sine 15 degrees, and we're on degrees, 7.76. And what I might just do, because I was keeping a few more decimal places for the other one, so 7.765, 0.76. So I'll just keep 4 significant figures for now, just so I get a more accurate answer at the end. So we've figured out x2, now we want y2. So if we're using this 15, we've got adjacent and hypotenuse here. And so adjacent over hypotenuse is cos, so katoa cos. So therefore this time we've got cos 15 degrees is adjacent over hypotenuse. Cos 15 degrees is equal to y2 over 30. So therefore y2 is equal to 30 cos 15, which is equal to, no, that's right. So 30 times cos 15 is 28.97, 28.98 to 4 significant figures, 28.98. Forgotten my units here. Double check that. Okay. Okay. Just doing a quick check on these to make sure they look sensible. So I'm not doing a careful check, just a quick check. So that's 40. These two must be less than that because that's the hypotenuse. This is 30 degrees, so this one's going to be pretty small. The reason this one turned out to be 20 is another rule that's worth knowing. If you've got an equilateral triangle, each of those angles is going to be 60 degrees because they're all the same. They add up to 180. So you get an if you cut that in half, you get 2 right angled triangles. The length of this is going to be 2. The total length of that is going to be exactly the same because it's also equilateral. So this is going to be 1. And that's what we've got in this case. This here was 30 degrees. So that's half of the 60 degrees that made that up. And so this was 40. Let me just rub that out. So the other one must be half of that because it's essentially half of an equilateral triangle. So that's why that ended up to be a nice round number. And no big deal, you don't have to remember that, but it's just handy to keep an eye on these things. Helps to check your answers. But anyway, so that one's pretty much right if that one's right. X2, and so again, X is pretty small, so that makes sense. Y2 is going to be somewhere very close to this number. Because if you imagine swinging that round, it's not an awful lot shorter than that one, but it is shorter. So those answers look okay. Now, next step is we add together the x components. So we said we want to try and find the x and y component of the resultant vector. So that's this vector here. So your x component was along here. The diagram's getting a bit messy, sorry. you've got your y component through here. So we'll call this x total and y total. So you can see that this x total is just this x1 plus this x2, and your y total is just this y1 plus this y2. And so we can say x total is equal to x1 plus x2, which is equal to 34.64 plus 7.765, which is equal to, just kind of make this a wee bit smaller so that we can see it. So we've got 34.64 plus 7.765. And I'll keep it to I'll keep it to 4 significant figures. I'll round to the even number. So that's going to be 42.40 millimeters. Seems reasonable. Y total is equal to y1 plus y2. So this whole y component here is just the sum of this one plus the sum of this one. So y1 plus y2, which is equal to 20 plus 28.98, which is equal to 48.98 millimeters. Okay, let's just redraw, or do we have to? Yeah, we should. Let's just quickly redraw that. I'm not going to do it to scale, but I'll just do a very quick sketch of that resultant. So I'm taking x total like so, y total like so, and the resultant goes between them. So this here is just this here. I'm just redrawing it just so we can see what we're doing. So x total is 42.4, y total is 48.98, and we want to figure out, what am I going to call this? Let's just call it t. Why not? Okay, so this time we've got two sides. We want the other side, so we want to go for Pythagoras, and we should label. So by now you might not need to do this every time, but that's C on this side. A and B don't matter. So the formula is C squared equals A squared plus B squared, which is equal to 42.40 squared plus, this is C squared, just so I don't forget it's not C, plus 48.98 squared. So therefore C is going to be the square root of both of those things, so the square root of the whole side, which is not the same as taking the square root of each of them. So then we'll just put that in. So square root of 42.40 squared plus 48.98 squared (64.78 millimeters), and we'll just do it to 3 significant figures, so it's 64.8. Okay, so what were we asked again? So let's go back to the question. One thing we can do is we can check if it looks reasonable. So by scale, I got 65, got 64.8. It's pretty close, closer than I expected, to be honest. And so that looks pretty good. And we still had to get the direction, so we found the magnitude. Now we need to get the direction. So we'll take it clockwise from the x-axis again. We'll call it theta. Keep using, well, this case we've got nothing we were given. We've calculated everything, so it doesn't really matter what we use. I'll use tan probably. So we'll just put on sine, cos, tan letters. So that's opposite. The right angle is the hypotenuse, opposite the angle is opposite, and adjacent to the angle is adjacent. So tan theta is equal to TOA, opposite, over adjacent. So tan theta is equal to opposite 48.98 divided by 42.40. Just going to move this up a bit. So tan theta is that, so therefore theta must be the inverse tan of that. Tan to the minus 1, or a tan, 48.98 over 42.40, which equals it's the same as before, tan to the minus 1, but in here I need to write, the little calc pad wants you to write a tan, 48.98 divided by 42.40. It was 49.1 degrees. And we're done. Was that what we got before? Yes, it was. It's anti-clockwise, so I'm just looking up here, and we got 49 degrees just from the scale drawn. We've calculated as 49.1 degrees. So you can see the scale drawn might not be accurate, but it's a lot quicker than doing all the calculations. Okay, so write out the answer in short form. So magnitude of resultant is 64.8 millimeters. Actually, let's just check what the question said again. Magnitude and direction. Yeah, magnitude of the resultant is 64.8 millimeters at 49.1 degrees anti-clockwise from the x-axis. And we're done.